According to the National Electrical Code, specifically Section 250.61 B2, a grounding electrode conductor, often abbreviated as GC, shall be connected to the equipment grounding conductor EG inside or at the service equipment. The traditional method involves running the grounding electrode conductor out of the meter can or the main breaker at the house. An alternative method involves running the grounding electrode conductor from the neutral at the top of the pole or before the weatherhead at the house, straight down to the ground rods. While it is true that running the grounding electrode conductor from a higher point provides better lightning protection, it is not a common practice and is not specifically required by the National Electrical Code. For the pole, it is recommended to follow the National Electrical Code and run the grounding electrode conductor from the bottom of the meter can or the main breaker at the pole. For the house, connect the grounding electrode conductor to the neutral at the top of the weatherhead and terminate it at the grounding electrode system near the foundation of the house. There are advantages of running the grounding electrode conductor to the top of the weatherhead at the house. Firstly, reduced risk of damage. If lightning strikes the weatherhead, the grounding electrode conductor will provide a direct path to ground, reducing the risk of damage to the electrical system inside the house. Secondly, enhanced lightning protection. The closer the grounding electrode conductor is to the point of lightning entry, the better it will protect the electrical system. While running the grounding electrode conductor from a higher point provides enhanced lightning protection, it is not a requirement. It is generally acceptable to follow the National Electrical Code guidelines and connect the grounding electrode conductor to the equipment grounding conductor at the service equipment. However, for optimal lightning protection, it is recommended to run the grounding electrode conductor from the top of the weatherhead at the house to the grounding electrode system. The grounding electrode conductor, or GEC, plays a crucial role in ensuring electrical safety and protecting electrical systems from faults and overvoltages. The primary function of the GEC is to connect the electrical system to the earth, providing a low impedance path for fault currents to flow back to the source. This connection to earth is essential for the proper operation of current protection devices, such as circuit breakers and fuses, which are designed to interrupt the flow of current in the event of a fault. The grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, ground plates, or underground metallic water pipes that are buried in the earth and connected to the GEC. The size and type of grounding electrode required depend on the size of the electrical system and the soil conditions at the site. The National Electrical Code, or NEC, provides detailed requirements for grounding and bonding electrical systems, including the size and installation of the GEC and the grounding electrode system. According to the NEC, the GEC must be sized based on the size of the service entrance conductors, with larger conductors requiring a larger GEC. The GEC must also be installed in a manner that provides a continuous and permanent connection to the grounding electrode. In addition to providing a path for fault currents, the GEC also helps to stabilize the voltage of the electrical system and reduce the risk of electric shock. By connecting the electrical system to earth, the GEC helps to equalize the potential between the electrical system and the surrounding environment, reducing the likelihood of a dangerous voltage difference. This is particularly important in areas where there is a high risk of lightning strikes or other electrical disturbances. Proper grounding and bonding are essential for ensuring the safety and reliability of electrical systems. By following the requirements of the NEC and other applicable standards, electrical contractors and installers can help to protect people and property from the hazards of electricity. There are several types of grounding electrodes commonly used in electrical systems, each with its own advantages and disadvantages. The most common types of grounding electrodes include ground rods, ground plates, and underground metallic water pipes. Ground rods are typically made of copper or copper-clad steel and are driven into the earth to provide connection to ground. Ground plates are flat metal plates that are buried in the earth and connected to the GEC. Underground metallic water pipes can also be used as grounding electrodes, provided that they are in direct contact with the earth for at least 10 feet and are electrically continuous. The choice of grounding electrode depends on several factors, including the soil conditions at the site, the size of the electrical system, and the local requirement. In areas with high soil resistivity, it may be necessary to use multiple grounding electrodes or to install chemical ground rods to improve the connection to ground. Chemical ground rods are filled with chemicals that help to reduce the soil resistivity and improve the conductivity of the grounding electrode. The installation of grounding electrodes must be performed in accordance with the requirements of the NEC and other applicable standards. Ground rods must be driven into the earth to a depth of at least 8 feet, and ground plates must be buried at least 30 inches below the surface. The GEC must be connected to the grounding electrode using a listed connector or clamp, and the connection must be protected from corrosion. In addition to the grounding electrode system, electrical systems also require a bonding system to ensure that all metal parts of the electrical system are electrically connected together. The bonding system helps to equalize the potential between different metal parts of the electrical system, reducing the risk of electric shock. The bonding system typically consists of bonding conductors that are connected to metal conduits, metal enclosures, and other metal parts of the electrical system. The bonding conductors must be sized based on the size of the circuit conductors, and they must be installed in a manner that provides a continuous and permanent connection. Proper grounding and bonding are essential for ensuring the safety and reliability of electrical systems. By following the requirements of the NEC and other applicable standards, electrical contractors and installers can help to protect people and property from the hazards of electricity. Let's delve deeper into the specific considerations for grounding at a yard pole and a house in a farm setting. Given the potential for lightning strikes in rural areas, robust grounding is paramount. At the yard pole, where the service enters, the primary objective is to establish a solid grounding reference point. This is typically achieved by driving one or more ground rods into the earth near the pole. The National Electrical Code mandates a minimum length and diameter for these ground rods, ensuring adequate contact with the soil. The grounding electrode conductor, size according to the service entrance conductors, connects the neutral conductor at the service disconnect to these ground rods. While connecting the grounding electrode conductor directly to the neutral at the top of the pole might seem like a more direct path for lightning, it deviates from standard practice and could introduce complexities in meeting inspection requirements. Therefore, adhering to the NEC and connecting the grounding electrode conductor to the neutral within the meter canal service disconnect is generally recommended. For the house, the grounding strategy involves establishing a grounding electrode system, which can include ground rods, a ground ring, or a connection to a metallic water pipe, if available and properly bonded. The grounding electrode conductor connects the neutral busbar in the main service panel to this grounding electrode system. A key consideration is the proximity of the grounding electrode system to the house. The closer the grounding electrode system is to the house, the more effective it will be in dissipating lightning strikes and other transient voltages. Running a separate grounding electrode conductor from the weatherhead directly to ground rods, as suggested, can indeed provide enhanced lightning protection. This approach creates a more direct path to ground for any surge that enters the system via the overhead service conductors. However, it's crucial to ensure that this additional grounding electrode conductor is properly bonded to the main grounding electrode system at the house. This ensures that all grounding points are at the same potential, preventing voltage differences that could create hazardous conditions. The size of the supplemental grounding electrode conductor should be determined based on the size of the service entrance conductors, as per the NEC guidelines. Furthermore, it's essential to use appropriate connectors and methods for attaching the grounding electrode conductor to the weatherhead and the ground rods. The connections must be secure, corrosion-resistant, and suitable for direct burial. In addition to the grounding electrode system, bonding is crucial for ensuring electrical safety. All metallic components of the electrical system, such as metal conduits, enclosures, and equipment frames, must be properly bonded together and connected to the grounding electrode system. This creates a low impedance path for fault currents, allowing overcurrent protection devices to quickly trip and clear any faults. When upgrading the service entrance conductors, it's important to ensure that the grounding and bonding system is also upgraded to meet the new requirements. This may involve replacing the grounding electrode conductor with a larger size or adding additional ground rods to the grounding electrode system. It's also crucial to inspect and verify the integrity of the existing bonding system, ensuring that all connections are tight and corrosion-free. Considering the specific context of a farm, where there may be multiple buildings and electrical systems, a comprehensive grounding and bonding plan is essential. Each building should have its own grounding electrode system, and all buildings should be interconnected with a bonding conductor. This helps to equalize the potential between the different buildings and provides a common grounding reference point. Furthermore, it's important to consider the presence of any livestock or other sensitive equipment on the farm. These may be particularly vulnerable to voltage surges and other electrical disturbances. Therefore, additional surge protection devices may be necessary to protect these assets. Surge protection devices, or SPDs, are designed to divert transient voltages away from sensitive equipment, preventing damage and ensuring reliable operation. SPD should be installed at the service entrance and at any other points where sensitive equipment is connected to the electrical system. In conclusion, grounding and bonding are critical for ensuring electrical safety and protecting electrical systems from faults and overvoltages. By following the requirements of the NEC and other applicable standards, electrical contractors and installers can help to protect people and property from the hazards of electricity. In a farm setting, where there is a higher risk of lightning strikes and other electrical disturbances, robust grounding and bonding are particularly important. This may involve running a separate grounding electrode conductor from the weatherhead directly to ground rods, provided that it is properly bonded to the main grounding electrode system. It's also essential to consider the presence of any livestock or other sensitive equipment and to install surge protection devices as needed. Always consult with a qualified electrical contractor to ensure that the grounding and bonding system is properly designed and installed. The information provided here is for general guidance only and should not be considered a substitute for professional electrical advice. The National Electrical Code, or NEC, serves as the cornerstone for safe electrical installations. It provides comprehensive guidelines for grounding and bonding, and adhering to its requirements is essential for ensuring electrical safety. Let's delve into some specific NEC articles that are particularly relevant to this scenario. Article 250 covers grounding and bonding in detail. It outlines the requirements for grounding electrode systems, grounding electrode conductors, and equipment grounding conductors. Understanding the requirements in Article 250 is crucial for designing and installing a safe and effective grounding system. Section 250.24 addresses grounding service supplied alternating current systems. It specifies the requirements for grounding the neutral conductor at the service entrance, as well as the sizing and installation of the grounding electrode conductor. Section 250.50 covers grounding electrode systems. It lists the types of grounding electrodes that are permitted by the NEC, such as ground rods, ground plates, and underground metallic water pipes. It also specifies the requirements for the size and installation of these grounding electrodes. Section 250.66 provides guidance on sizing the grounding electrode conductor. It specifies the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. Section 250.104 addresses bonding of piping systems and exposed structural metal. It requires that metal water pipes, gas pipes, and structural metal be bonded to the grounding electrode system to ensure electrical continuity. In addition to these specific NEC articles, it's also important to be aware of other relevant codes and standards, such as local building codes and utility company requirements. These codes and standards may impose additional requirements for grounding and bonding. When designing and installing a grounding system, it's essential to consider the specific conditions at the site, such as soil conditions, the presence of underground utilities, and the potential for lightning strikes. These factors can influence the type and size of grounding electrodes that are required, as well as the overall design of the grounding system. For example, in areas with high soil resistivity, it may be necessary to use multiple grounding electrodes or to install chemical ground rods to improve the connection to ground. In areas where there is a high risk of lightning strikes, it may be necessary to install additional surge protection devices to protect sensitive equipment. Proper grounding and bonding are essential for ensuring electrical safety and protecting electrical systems from faults and overvoltages. By following the requirements of the NEC and other applicable codes and standards, electrical contractors and installers can help to protect people and property from the hazards of electricity. Always consult with a qualified electrical contractor to ensure that the grounding and bonding system is properly designed and installed. The information provided here is for general guidance only and should not be considered a substitute for professional electrical advice. Let's consider the role of the equipment grounding conductor, or EG, in conjunction with the grounding electrode conductor, or GEC, for a comprehensive understanding of electrical safety. The equipment grounding conductor, or EG, is a critical component of the grounding system that provides a low impedance path for fault currents to flow back to the source. The primary purpose of the EGC is to ensure that metal parts of electrical equipment, such as enclosures, raceways, and equipment frames, are at the same electrical potential as the grounded neutral conductor. This minimizes the risk of electric shock if a fault occurs. The EGC is typically a wire, conduit, or other conductive material that is run along with the circuit conductors. It is connected to the metal parts of the electrical equipment and to the grounding bus in the electrical panel. In the event of a ground fault, the EGC provides a path for the fault current to flow back to the source, causing the overcurrent protection device, such as a circuit breaker or fuse, to trip and de-energize the circuit. The size of the EGC is determined based on the size of the circuit conductors, as specified in the National Electrical Code, or NEC. The NEC provides tables that list the minimum size of the EGC for various circuit conductor sizes. It is important to use the correct size EGC to ensure that it can safely carry the fault current. In addition to providing a path for fault currents, the EGC also helps to reduce electrical noise and interference. By providing a low impedance path to ground, the EGC can help to dissipate unwanted electrical signals that can interfere with the operation of sensitive electronic equipment. The EGC must be properly installed and maintained to ensure that it is effective. All connections must be tight and corrosion-free, and the EGC must be protected from damage. It is also important to ensure that the EGC is properly bonded to the metal parts of the electrical equipment and to the grounding bus in the electrical panel. Bonding is the process of connecting metal parts of the electrical system together to create a low impedance path for fault currents. Bonding helps to ensure that all metal parts are at the same electrical potential, reducing the risk of electric shock. The NEC provides detailed requirements for bonding electrical systems. These requirements specify the types of bonding conductors that are permitted, as well as the methods for making bonding connections. Proper grounding and bonding are essential for ensuring electrical safety and protecting electrical systems from faults and overvoltages. By following the requirements of the NEC and other applicable codes and standards, electrical contractors and installers can help to protect people and property from the hazards of electricity. Always consult with a qualified electrical contractor to ensure that the grounding and bonding system is properly designed and installed. The information provided here is for general guidance only and should not be considered a substitute for professional electrical advice. Let's address surge protection devices, or SPDs, and their role in safeguarding electrical systems from transient overvoltages, especially in environments prone to lightning strikes, like farms. Surge protection devices, or SPDs, are designed to protect electrical equipment from transient overvoltages, such as those caused by lightning strikes, utility switching, and other electrical disturbances. These overvoltages can damage sensitive electronic equipment, such as computers, televisions, and appliances, and can even cause fires. SPD work by diverting the surge current away from the protected equipment and to ground. When a surge occurs, the SPD clamps the voltage to a safe level, preventing it from reaching the protected equipment. There are several types of SPD available, each with its own characteristics and applications. The most common types of SPD include whole house surge protectors, which are installed at the service entrance, and point-of-view surge protectors, which are installed at individual outlets or equipment. Whole house surge protectors provide protection for the entire electrical system, while point-of-use surge protectors provide protection for specific equipment. The choice of SPD depends on the level of protection that is required in the budget. It is generally recommended to install a whole house surge protector to protect the entire electrical system, and then supplement it with point-of-use surge protectors for sensitive equipment. SPD are rated by their surge current capacity, which is the maximum amount of current that they can safely divert. The higher the surge current capacity, the better the protection. SPD are also rated by their voltage protection rating, or volts, which is the maximum voltage that they will allow to pass through to the protected equipment. The lower the voltage protection rating, the better the protection. When selecting an SPD, it is important to choose one that is appropriate for the voltage and current requirements of the electrical system. It is also important to choose an SPD that is listed by a recognized testing laboratory such as Underwriters Laboratories, or UL. SPD should be installed by a qualified electrical contractor in accordance with the manufacturer's instructions and the National Electrical Code, or NEC. SPD should be installed as close as possible to the equipment that they are protecting. It is also important to ensure that the SPD is properly grounded. SPD have a limited lifespan and will eventually need to be replaced. Most SPD have an indicator that shows when they have reached the end of their lifespan. It is important to check the SPD regularly and replace it when necessary. Surge protection is an important part of a comprehensive electrical safety plan. By installing SPD, you can protect your electrical equipment from damage caused by transient overvoltages and reduce the risk of fires. The use of 1/0 neutral supported triplex cable with XLP insulation for the overhead service conductors with a 205 amps rating provides a durable and weather-resistant solution for delivering power from the odd pole to the house. XLP insulation, or cross-linked polyethylene insulation, is known for its excellent electrical properties, high temperature resistance, and resistance to moisture and chemicals. This makes it a suitable choice for outdoor applications where the cable will be exposed to the elements. The 1/0 American wire gauge, or AUG, size is appropriate for 200 amps service, as it has an ampacity that exceeds the service rating. However, it's crucial to verify the ampacity of the cable based on the specific installation conditions, such as the ambient temperature and the number of conductors bundled together. The NEC provides ampacity tables that can be used to determine the appropriate conductor size for various installation conditions. The neutral supported configuration of the triplex cable provides mechanical support for the conductors, reducing the need for separate messenger wires. This simplifies the installation process and reduces the overall cost. The installation of the triplex cable should be performed in accordance with the NEC and other applicable codes and standards. The cable should be properly supported and secured to prevent sagging and damage. The connections at the weatherhead and the service entrance should be made using appropriate connectors that are listed for use with XLP insulated conductors. When transitioning from the overhead service conductors to the underground service entrance cable, it is important to use a suitable transition fitting that is designed to protect the conductors from moisture and mechanical damage. The underground service entrance cable should be buried at the proper depth, as specified in the NEC, to protect it from physical damage. It is also important to mark the location of the underground cable to prevent accidental damage during excavation. The use of 1/0 neutral supported triplex cable with XLP insulation is a good choice for upgrading the overhead service conductors. However, it is important to verify the ampacity of the cable based on the specific installation conditions and to follow the NEC and other applicable codes and standards during the installation process. The new service entrance cable running down to a new 200 amps breaker mounted in the corner of the house, then service entrance cable running through the crawl space to the panel board in the basement represents a common and code-compliant method for delivering power to the house. Mounting the 200 amps breaker on the exterior of the house provides a convenient disconnect point for the service. This allows the homeowner to easily disconnect power to the entire house in the event of an emergency or for maintenance purposes. The breaker should be installed in a weatherproof enclosure that is suitable for outdoor use. The service entrance cable, or SEC, that runs from the breaker to the panel board in the basement should be sized according to the service rating and the NEC requirements. The SEC should be protected from physical damage and should be properly supported along its run. When running the SEC through the crawl space, it is important to protect it from moisture and rodents. The cable should be supported above the crawl space floor and should be protected from sharp objects. The panel board in the basement should be sized to accommodate the existing and future electrical loads of the house. The panel board should be properly grounded and bonded, and all circuits should be clearly labeled. The installation of the new service entrance cable and panel board should be performed by a qualified electrical contractor in accordance with the NEC and other applicable codes and standards. It is important to obtain the necessary permits and inspections to ensure that the installation is safe and code compliant. The service entrance cable, often abbreviated SEC, carries the electrical power from the utility company's service drop to the main service panel inside a building. It is a critical component of the electrical system, and its proper installation is essential for safety and reliability. There are two main types of SEC wiring methods. Firstly, service entrance cable with a bare neutral conductor, often referred to as SC cable, and secondly, service entrance cable with an insulated neutral conductor, often referred to as SCR cable. SC cable is typically used for above-ground installations, while SCR cable is typically used for underground installations or for interior wiring where the bare neutral conductor could pose a safety hazard. The size of the SEC depends on the size of the service, which is determined by the total electrical load of the building. The National Electrical Code, or NEC, provides tables that list the minimum size of the SEC for various service sizes. It is important to use the correct size SEC to ensure that it can safely carry the electrical current. The SEC must be protected from physical damage and must be properly supported along its run. The NEC provides detailed requirements for the installation of SEC, including the types of supports that are permitted and the spacing between supports. The SEC must also be properly grounded and bonded to ensure that it is at the same electrical potential as the grounded neutral conductor. This helps to prevent electric shock if a fault occurs. The NEC provides detailed requirements for grounding and bonding SEC. The connections at the service entrance and the main service panel must be made using appropriate connectors that are listed for use with SEC. The connections must be tight and corrosion-free to ensure a reliable electrical connection. The installation of SEC should be performed by a qualified electrical contractor in accordance with the NEC and other applicable codes and standards. It is important to obtain the necessary permits and inspections to ensure that the installation is safe and code compliant. The service entrance panel, often abbreviated SEP, is the main distribution point for electricity in a building. It receives power from the service entrance cable and distributes it to the various branch circuits throughout the building. The SEP contains the main breaker, which is used to disconnect power to the entire building. It also contains the circuit breakers or fuses that protect the individual branch circuits. The size of the SEP depends on the total electrical load of the building. The NEC provides guidelines for calculating the electrical load of a building and for selecting the appropriate size SEP. The SEP must be properly grounded and bonded to ensure that it is at the same electrical potential as the grounded neutral conductor. This helps to prevent electric shock if a fault occurs. The NEC provides detailed requirements for grounding and bonding SEP. The SEP must be installed in a location that is readily accessible and protected from physical damage. It should also be installed in a dry location to prevent corrosion. The installation of the SEP should be performed by a qualified electrical contractor in accordance with the NEC and other applicable codes and standards. It is important to obtain the necessary permits and inspections to ensure that the installation is safe and code compliant. It is essential to highlight the importance of adhering to local codes and obtaining necessary permits before commencing any electrical work. Local codes may have specific requirements that go beyond the National Electrical Code, or NEC, and these requirements must be followed to ensure compliance. Obtaining permits is also crucial as it allows the local authorities to inspect the work and ensure that it is being done safely and in accordance with the applicable codes. The permit process typically involves submitting plans and specifications for the electrical work to the local building department. The plans are reviewed to ensure that they meet the code requirements, and a permit is issued if they are approved. Once the electrical work is completed, it must be inspected by the local building department to ensure that it was done properly. If the work passes inspection, a certificate of occupancy is issued, which allows the building to be occupied. Failure to obtain permits and inspections can result in fines, delays, and even legal action. It can also create a dangerous situation, as the electrical work may not be up to code and could pose a safety hazard. Therefore, it is always recommended to consult with a qualified electrical contractor and to obtain the necessary permits before starting any electrical work. The electrical contractor will be familiar with the local codes and permit requirements and can help to ensure that the work is done safely and in accordance with the applicable regulations. Furthermore, it is important to maintain accurate records of all electrical work that is performed. These records should include the plans and specifications, the permits, the inspection reports, and any other relevant documents. These records can be helpful in the future if there are any questions or problems with the electrical system. In conclusion, adhering to local codes and obtaining necessary permits are essential for ensuring the safety and compliance of electrical work. It is always recommended to consult with a qualified electrical contractor and to follow the guidance throughout the process.